Okay, so as I said, I'm a mathematician from the University of Zagreb, so my research is mostly in field of partial differential equations and mathematical modeling using partial differential equations. Now, today's talk is about a simple problem of heat exchange between some vessel which contains fluid and the exterior medium. So this appears in many applications. For example, you have some pipe with fluid which is hot inside, and the exterior medium is, say, cold. So there is a heat exchange between the fluid inside and the exterior medium. It appears frequently in many heat exchangers in industrial uh, facilities, but also in, for example, human body, because human body has a very clever way of regulating our temperature, which also includes the heat exchange between the blood vessels and the exterior tissue. So the typical situation is you, for example, put warm fluid in a pipe and the exterior medium is cold, so there is a cooling process. It could be the vice versa, the fluid could be cold and the medium could be hot. It doesn't really matter for this purpose. Now, typically what you would do is uh, you would just neglect the pipe of the wall because it is tiny and the process inside is very fast. And you just impose some kind of boundary condition between the fluid and the exterior medium by neglecting just the wall of the pipe. What I'm about to tell you is that this is not the best idea because sometimes the wall of the pipe is also a significant part of the process because it has a life of its own. It could be very important. Now, as you know, pipes could be made of different materials. It could be a metal, but it also could be a plastic or concrete. So there is a very large difference between the heat conducting properties of the different kind of the pipes, and those should be included in the models. So just some notations. Alpha here is the coefficient which appears in the heat conduction equation. So we usually call it the diffusivity coefficient. It's actually defined as the ratio between the heat conductivity and the density of the fluid and the specific capacity of the fluid. Now, this alpha, which appears in the heat conduction equation, can be very different depending on the material the pipe is made. For example, if you have a copper pipe, it would be of order 10 on minus 4 because the copper is highly conductive. Steel 10 on minus 5, so a little bit less. But if it's aluminum, it would be 10 on minus 7. Uh, for example, if it's a PVC, it's almost isolating, so 10 minus 8 because plastic conducts very poorly, and so does the rubber. So the ratio between the thermal diffusivity of the pipe and the wall of the pipe can be huge, can be up to 10 on power 4 or as low as 10 on minus 1, depending on what kind of fluid you put in which kind of pipe. So to describe this ratio between the conductivities of the pipe wall and the fluid which is inside, we introduce a small parameter which is denoted by epsilon and which is the ratio between those two. Now, let me go a little bit about the geometry. So typically the wall of the pipe would be much tinier than the pipe itself. So I denote by P1 the inside of the pipe and by P epsilon the wall of the pipe. And the whole thing together is P1 plus epsilon. Okay. It's a cylindric pipe for purpose of this presentation, but it could be of any shape, doesn't really matter. Now, as I said, the diffusivity coefficient of the solid part, meaning the wall of the pipe, and the diffusivity coefficient of the fluid which is inside the pipe is assumed to depend on this same parameter epsilon. It doesn't really mean that they are physically related. It just means that they have a similar quantity. So this is just a quantitative assumption, not qualitative. We don't really think that those parameters are physically related. We just think that they are of the same order. Now, the exponent Q here determines what kind of pipe we are talking about. So if Q is small, it means that this ratio is smaller. If Q is large, the other way around. If Q is large, meaning that this ratio is small, because epsilon is a small parameter. And if Q is, for example, negative, it means that this number is large. Now, depending on this ratio, we propose several different models for modeling this particular situation. Now, the equation is just the convection diffusion equation. So you have Laplacian, which is describing the diffusion, and then you have the convective part. V here is the convection velocity, which in a pipe would typically be of the Poisson form, so it's a parabolic profile typical for the pipe, if we are talking about viscous fluid. And then on the wall of the pipe, we have a heat exchange, which says that the loss of the temperature is proportional to the difference between the outer temperature G and the inside temperature theta. Now, theta depends on epsilon, which is the thickness of the wall. And R here is the dimensionless coefficient, because the equations are written in a dimensionless form. Okay. Now, on the ends of the pipe, you can impose any kind of boundary condition, Dirichlet, Neumann, Robin, whatever. So for the purpose of this research, we just say that it's a Neumann condition, so it's isolated on the ends, but it doesn't really matter for the model. Now, if you write your equations in a weak form, which would be typical if you are using finite element for simulations, it looks like this. And those coefficients epsilon appear here and there. There is the part of the variational form of our equation which appears on the wall of the pipe. So the integral here is over the fluid, and the integral here is over the solid wall of the pipe. Now, what do we get when we let epsilon approaching 0, which means that the pipe is tiny? Now, you would expect that just the wall of the pipe disappears from the limit, but it's not necessarily the case. It depends on how high the conductivity is. So this is just mathematics, so you can neglect it. The convergence of the temperature to the macroscopic model is in some technical space, which is called L infinity, doesn't really matter. And in any physical situation, the equation at the end is just the same as from the beginning. It's the heat conduction equation with the convective part. The difference is in the effective boundary condition, because what's going on is that you have the pipe with the wall of thickness epsilon. So if you let epsilon go to 0, the wall disappears, but the effective boundary condition remains. So in the geometrical sense, this thing disappears, but in the mathematical sense, it doesn't, because it leaves some trace in the boundary condition, which we call the effective boundary condition at the end. Now, we use some method which is called two-scale convergence. Doesn't really matter. It's pure mathematics. And we get 5 different models. Now, first model is when Q is smaller than -1. Q smaller than -1 meaning that the conductivity of the wall of the pipe is extremely high. So that would be, for example, a copper pipe. Now, in that case, the most of the heat is going through the pipe, not through the fluid, because the pipe is conducting much better than the fluid itself. So it means that the process that is going in the metal pipe part of the pipe is dominating. And what you get is you get some kind of non-local boundary condition, which says that your temperature on the wall of the pipe is basically constant. And this constant satisfies the condition, which is sort of Robin type, but in the mean value sense. So its derivative with respect to the radial variable is proportional to the difference of the mean temperature of the outside medium and the mean temperature of the fluid inside. Now, those are mean values, meaning we are taking integrals. And as I told you before, it basically means that the process in the wall of the pipe is so rapid that the temperature stabilizes to some constant value. And then this constant temperature outside satisfies this mean kind of boundary condition. Now, this is a model that's not known in the literature. And we don't really know how physical it is. Now, the other situation is when Q is equal to -1, which means that still the pipe is conducting rapidly, meaning it's some kind of metal, but not so fast as in the first case. In that case, there is a balance between the process inside the pipe, in the fluid, and in the wall of the pipe. And what we get is another heat conduction equation in the pipe's wall. And this one is actually in curvilinear coordinates because the pipe's wall is not flat, it's round. So the operator here is so-called Laplace-Beltrami operator, which means that the derivatives are happening only in tangential direction. And on the right-hand side, you have a difference between the outer temperature and the temperature on the wall. So you have two separate equations. One is inside the pipe and the other is on the wall. And those two processes are about of the same magnitude. Now, if Q is between -1 and 1, the parameter that I introduced in the model, that's the classical engineering case. That means that the pipe of the wall is conducting well, but not so high. So that would be, for example, a steel pipe. And in that case, you just can neglect the pipe. Okay, so as the pipe is tiny, you can forget about it and just impose the heat exchange condition between the fluid inside the pipe and the exterior medium by forgetting that the wall is there. So it means you have a Robin condition saying that the change of the temperature is proportional to the difference between the outer and the inner temperature, as in the model that we started with. Now that's the one that we expected to find. Now, if Q is equal to 1, so that's the right-hand side limit of the interval, then the model is still same, but this heat conduction coefficient, which is called the Nusselt number in the non-dimensional form, is a little bit lower. Okay, it has to be modified due to the fact that the pipe is starting to conduct a little poorly. Okay. And then finally, if the pipe is really conducting poorly, meaning we have a glass or plastic pipe, then basically it acts as an isolator. So there is no heat exchange, and that's the case when Q is superior to 1. So in that case, you just have that the normal derivative on the boundary is 0, meaning that there is no exchange between the pipe and the exterior medium. That's also what we expected. So what we did not expect are those previous models. Now, mathematically speaking, as I said, we just need to prove that the solution, which depends on spore parameter epsilon, tends to something when epsilon goes to 0. Now it does in some topology, which is called the weak star topology. I won't bother you too much with the details. What's important is that the limit model still has a unique solution, because if it doesn't, then the convergence doesn't mean much, because your sequence can diverge to the different cluster points. But in this case, it doesn't, because it's the solution of the limit problem is unique, meaning that we have a stable convergence. And the models, as I told you, are different between those 5 different cases. Now, let me just skip to the, this is for mathematicians, for numerical examples. So just to make you see what's really going on by doing some simulations, we picked the Q in 5 different regimes. So -1 meaning it's very conductive pipe, a -5, -1 meaning that the two processes are of the same order. So it's highly conductive, but not as high as in the first case. Now this is a typical engineering case where Q is equal to 0, meaning that the conductivity of the pipe and the conductivity of the fluid are about of the same order. Now when Q is equal to 1, meaning that the pipe is starting to act as an isolator, but still not completely isolating. And Q equal to 5, meaning that the conductivity is very low, meaning that it's almost isolating. Now, we took epsilon to be 2 on power -4. That's the thickness of the pipe wall. K is a coefficient in the heat conduction equation. We took it for simplicity to be equal to 1. The Peclet number is 0 because we neglected the convection, so it's pure diffusion. And let's see, Okay, so in a case when the wall of the pipe is highly conducting, there is nothing going on the fluid. So the temperature stabilizes very quickly to constant, and you can just see the homogeneous distribution of the temperature, which was predicted by the model. Now, when Q is between -1 and 1, it's more likely closer to the physics. And you can see that there is some conducting going on in the wall of the pipe, which is here, and also inside the fluid. And the transfer between the fluid and the wall is kind of continuous. Now, for Q equal to 0, that's the completely engineering model, meaning that the conductivity of the wall of the pipe and the fluid inside are of the same order, exactly the same, and you don't see the pipe appearing in the model at all. Now, next case is when pipe is starting to isolate a little bit, meaning that we are closer to non-metallic wall, for example, a glass wall which conducts heat but poorly. And then you can see that when the temperature approaches the wall of the pipe, the conduction is still going on, but it's a little bit slower, the process. You can see the jump here, almost. I mean, it's heat conduction equation. There is no jump. It's small. It's smooth, but you can see the discrepancy. And the last case is the case when Q is equal to 5. It means that the pipe is completely isolating the rest of the fluid from the process, and there is no heat exchange going on, okay, as predicted by the model. Now, just to finish, I would like to thank the Croatian Science Foundation, which financed the research. Thank you very much.